Welcome to This Explainer. Today, we're diving into something absolutely wild. We're going to unpack one of the most fascinating subjects in all of science, carbon. It's essentially the ultimate, incredibly friendly building block of our entire universe. If you've ever wondered how the natural world snaps together to create the complex structures we interact with every single day, well, you are definitely in the right place. Okay, let's kick things off with a pretty stark paradox. Despite its massive, undeniable importance, carbon makes up a practically invisible 0.02% of the Earth's crust in the form of minerals like coal and petroleum. And up in our atmosphere, just 0.03% as carbon dioxide. When you look at the raw numbers, it is staggeringly scarce. And that leads us to a really massive question. Despite this extreme scarcity, almost everything around us, the food we eat, the clothes we wear, the medicines we take, and literally all living structures, is based on this one incredibly versatile element. How is that even possible? How does carbon pull this off? Well, it all comes down to how it forms bonds. The secret lies right in its physical properties. When we look at common carbon compounds, things like acetic acid, chloroform, ethanol, and methane, their extremely low melting and boiling points reveal something absolutely crucial. They have very weak intermolecular forces. Plus, because these carbon compounds are basically non-conductors of electricity, it tells us they don't form ions. So how exactly are they connecting? They connect through what chemists call a covalent bond. You see, carbon has an atomic number of 6, which means it has 4 electrons sitting in its outermost shell. To reach a happy, stable state, it needs 4 more. Now, a lot of other elements try to forcefully steal or give away electrons, but that would take way too much energy for a tiny nucleus with only 6 protons to manage. So carbon acts as the ultimate team player. It overcomes this whole problem by simply sharing its valence electrons. And to brilliantly illustrate this concept of sharing, just consider how nitrogen behaves. 2 nitrogen atoms can share 3 pairs of electrons to form a triple bond, which allows both of them to become completely stable. Just like nitrogen, carbon uses this highly effective sharing method to build incredibly strong connections with other atoms. So here's how carbon actually applies this. Take a molecule of methane, for instance. Carbon uses its 4 outermost electrons to share with exactly 4 hydrogen atoms. It beautifully constructs this perfectly stable molecule where everyone is happy and everyone has a full outer shell. Methane, by the way, is a major component of the CNG fuel we use every day, and the whole thing is built entirely on this simple principle of sharing. This brings us to carbon's first real superpower, tetravalency. Because it has exactly 4 valence electrons, it essentially has 4 perfect connection points. Honestly, think of carbon like a master Lego brick just waiting to snap into place with up to 4 other pieces, whether they're other carbon atoms or elements like hydrogen, oxygen, or nitrogen. But carbon doesn't stop there. Its second unique property is called catenation. This is its ability to bond with itself to form massive, sprawling chains. Elements like silicon actually try to do this, but they end up with highly reactive, unstable chains. Carbon, though, has a distinct advantage. Its exceptionally small size allows its nucleus to hold those shared electrons incredibly tight, which makes these long carbon-to-carbon chains perfectly stable. Now, the way these carbon atoms bond to each other can result in dramatically different physical forms, which we call allotropes. It's crazy to think about, but changing just the structural shape of those carbon-to-carbon bonds completely transforms the material. On one hand, you have diamond, a rigid 3D structure that is literally the hardest substance known to man. On the other hand, you have graphite, hexagonal arrays placed in smooth, slippery layers that actually conduct electricity. 2 drastically different materials born out of the exact same element. And if that wasn't amazing enough, carbon can even arrange itself into a sphere made of exactly 60 atoms that looks exactly like a tiny football. This belongs to a class of carbon allotropes called fullerenes, specifically named Buckminster fullerene. That's a mouthful, right? It was named after the U.S. architect who designed geodesic domes that share this exact same striking shape. So, how do we actually construct these molecules on a basic level? Well, building an ethane molecule is incredibly simple. You literally just snap 2 carbon atoms together first with a single bond, and then plug the remaining empty slots with hydrogen atoms. When all the valencies are perfectly satisfied by single bonds, we call it a saturated compound. Because carbon and hydrogen are such good friends, we classify their creations into 3 main families of hydrocarbons. The alkanes are those perfectly satisfied saturated compounds with single bonds we just talked about. But we also have alkenes, which feature double bonds, and alkynes featuring triple bonds. And it's really worth noting that the unsaturated ones, the alkenes and alkynes, are much, much more chemically reactive than the saturated alkanes. But what happens when we simply don't have enough hydrogen to go around? Say we're trying to build ethene. We link 2 carbons, but we only have 4 hydrogens to share. That leaves empty connection points. So what happens? Carbon simply adapts. It forms a double bond with its neighboring carbon atom, making absolutely sure every single connection requirement is perfectly satisfied. Carbon is so deeply versatile that you can take the exact same number of atoms and build completely different skeletal shapes. Take butane, for example, which has 4 carbons and 10 hydrogens. You can snap them together in one long straight line, or you can build a branched skeleton. Chemists call these completely different structures born from the same formula structural isomers. And if straight lines and branches weren't enough architectural freedom for you, these carbon chains can actually loop back on themselves. They literally bite their own tails to form perfect geometric rings. Whether it's saturated like cyclohexane or unsaturated like benzene, carbon handles these complex looping architectures with incredible stability. Now, carbon doesn't just play well with itself and hydrogen. It's incredibly friendly and will happily swap out a hydrogen atom to bond with specific atoms we call heteroatoms. Things like halogens, oxygen, nitrogen, or sulfur. When these specific groups of atoms attach to the carbon chain, they form what we call functional groups. And this is absolutely vital to understand. Once one of these functional groups attaches to the carbon chain, it acts as the new boss. Whether it's an alcohol group or a ketone group, it completely dictates the chemical properties of the entire molecule, regardless of how long the carbon chain itself is. Because of this functional group dominance, chemists can effectively organize these molecules into what's called a homologous series. In these series, the chemical properties remain essentially identical from one molecule to the next, even as the carbon chain gets longer and longer, by adding CH2 units, which gradually increases physical properties, like their melting and boiling points. Now, since there are literally millions of organic compounds, the sheer volume of them might seem a bit overwhelming. But don't worry, they are all named using a highly logical step-by-step system. You just count the carbons in the skeleton to get your base name, identify the functional group to find your suffix or prefix, and combine them. So a 3-carbon chain with a ketone group simply becomes propane plus -one, giving us propanone. It is a really elegantly structured system for an elegantly structured element. We've seen how tetravalency and catenation allow this incredibly tiny, scarce element to stretch out, share nicely with others, and build endless configurations. So knowing that this master builder element uses its unique friendly properties to form the foundation of our entire existence, I want to leave you with this thought to explore. Look around the room you are in right now and see if you can spot a single everyday item that isn't built on a foundation of carbon. Thanks for learning with me today on this explainer, and keep questioning the building blocks of your world.